All right, people, welcome. A few years ago, I was talking to an engineer and he's like, oh, you poor machine learning people. Back in the day, it was important to have all these machine learning skills because everyone had to write their own algorithms, and so it was really hard to do machine learning. But that's not true anymore because now there's all these great tools. You can just take any data set, drop it into a machine learning tool, get a model. Anybody can do machine learning, and I'm really sorry for you machine learning people who wasted all that time getting those skills. Whew, boy, do I wish that was true. How much I would love to have my job taken away by a computer where I just drop in some data and get a perfect model back, but it's not that easy. And so what I'm going to talk about here are the basics of what it takes to go from a data set with labels and a machine learning algorithm and produce a model that is very effective at the task that you're trying to accomplish. So what are we talking about here? Here's an overview of what it takes to build a model and ship it into production. You got to understand your application, do some feature engineering, plan a hyperparameter tuning run, execute it. You got to relax because that's going to take a long time. So drink some coffee, go for a walk, something like that. Don't get too stressed out. Then when the runs are done, you have to visualize the output of the runs and figure out, well, what is this telling me? Is the model that I produced a good one, or do I need to do some more work to make the model get better? What really happens is this little rat's nest here. And you end up bouncing from step to step, looking at the output, looking at your intermediate results and deciding, oh, geez, this isn't working out. Got to tweak something. I got to tune something. I got to go back and rerun part of the process. What I'm going to talk about today is a little bit of how you navigate these dotted lines in this little box called iterate and make a decision about when to iterate, but more importantly, what to do when you go and iterate. There are a few things that can help you understand this discussion that I'm going to give today, and I'll put links to free online lectures that can teach you some basic concepts that might help. Number one is error bounds and generalization. Number two is bias and variance. And number three is basic neural network architectures. So I'll link those videos below. If anything I'm saying here is starting to sound a little bit kind of like, what's he talking about? It's because I'm talking in shorthand now. Go watch those videos to learn the basics and then come back and apply those to learning how to tweak and tune models in practice. So the hard thing about building a model is that you bring your fanciest algorithm, you bring a bunch of data, and you want to apply a lot of power to the problem. Big GPUs, deep neural networks, all this stuff, it'll be fantastic. But the problem with machine learning is that everything's a balancing act. And this is about the bias variance trade-off or overfitting versus underfitting. An effective model tuning process, you're going to balance the data you have, the complexity of what you're trying to learn, all the feature engineering tools and tricks that you're able to throw at the problem, the model type and structure that you're doing, along with all the parameters to control that modeling process, the bias and variance, and computational realities, because you simply will not have enough time to run everything that you might like to run. So we're going to go through this in the context of an application. The application we're going to use to demonstrate this model tuning stuff is a very simple computer vision one. It's to take an image of an eye and to predict whether the eye is open or closed. So this is an online data set you can download for free. I'll provide a link, but there's about 4,500 images, so it's a pretty small data set. Each image is 24 pixels by 24 pixels, grayscale, a crop on an eye, and the labels are open or closed, whether the eye is open or closed. So the first step to building a great model is understand your data. Get a bunch of images like this, like I have on the side here, and look at them. Just pour through the images, look at as many as you can stomach, and ask yourself, is there anything interesting in these images that I'm looking at? Anything that should change what I want to do? So, well, here's an image where it's hard to tell if it's open or closed, so maybe that'll be a little bit challenging. Here's an image with some bangs falling over the eye, so they're not perfect, just an eye. There's a lot of stuff going on. Some of the images have glasses. There's some distortions in the image, not perfect stuff, so you're going to have to realize that you're going to need to deal with some noise and some distractors. There's a shark eye. I don't know who that is, but that eye looks kind of creepy to me. Not too much white around it. So if we're going to do a convolutional neural network, and remember, if you don't know what that means, go watch the video. But if we're doing a convolutional neural network, a filter size of 12 by 12 looks about like that. And so why would you want to know that? You'd want to say, well, would that filter be able to see things in the image that would help a machine learning system make a prediction? Or is the filter too small or too big, compared to the thing that we're trying to predict on? So 12 by 12 looks pretty big compared to an eye. 6 by 6, yeah, that's a reasonable size. So we can learn from this that, pretty small filters can identify important things in the data. Okay, there you go. put that in the bank. Another thing we can tell is like, look at this eye here in the bottom left, and then look at this thing right there. Well, it's actually a flip. And so one thing about the eyes is that if we flip them on the horizontal axis, a left eye can turn into a right eye. So we can potentially double our training data with that simple augmentation. And we'll see later on when and how that could be useful. Another good thing to do at this point is to run a really simple machine learning algorithm on the data and see where you're going to get to. So great, run a simple single layer fully connected neural network with 5 nodes, and you see that you have about 90% accuracy. And so what does this tell us? This tells us that we're going to be looking for final accuracies in the range of 92, 93, 94, 97, 98%. But what this also means is that the accuracy range is already sort of compressed up near 100%. And that means that as we try more and more sophisticated models, they're only going to be increasing the accuracy a very small amount. 92 to 93 is going to be a big step. 94 to 95 is going to be a huge step. And that gives us a sense of how powerful we need to make our statistical tests so we can tell that we're heading in the right direction. The next thing we want to do is pick a model structure. I'm basing this little discussion on an important but slightly older neural network structure. That's just to keep things simple, and also because we really are dealing with a pretty small problem here, 4,000 training examples. So we can't necessarily go to the biggest, greatest deep neural network or Inception Towers or some of the latest technology. And we'll see later on why we can't get there, but just to let you know, that's why we're starting here. So a little visualization of the neural network that we're going to use. We start with the input layer. Then we have a convolutional layer. And so the parameters here are N1, which is the dimension of the filter. That is 3 by 3, 5 by 5, 7 by 7, and also the number of filters that you want to have in the first convolutional layer. So already we've introduced 2 parameters that we're going to have to tune to produce the best possible model. The next thing that our neural network structure is going to have is a max pooling layer. There's no additional parameters here, but it does cut the input size down from 24 by 24 to 12 by 12. The next thing that we're going to have is a hidden layer and a dropout just before that. And so here's another parameter, H, which is the number of nodes to have in the hidden layer. And then there's going to be a single output layer, a single node in the output layer with a sigmoid. And then that's going to be interpreted as the probability that the eye in the image is open. We will also look at having an optional second convolutional block. And there's another convolutional layer with new parameters, the size of the filter in the second layer and the number of filters in the second layer. And then this will introduce another max pooling layer. So that's optional. We'll tune with it and without it and answer the question of, hey, is that actually a good thing to do? Will we get a better model by adding a second convolutional layer or not? Interesting question. I'll show you how to figure it out. So that gives us these parameters that are listed in the upper right there. 1, 2, 3, 4, 5, 6 parameters. And in the lower right, there's other things that we could change, other parameters that you might explore, just to give you a sense of the amount of tweaking and tuning you can use to get a really good model, but we won't worry about those too much. Okay, so now we have some data. Now we've picked a neural network structure, which has been proven to work pretty well in computer vision tasks. So what's so hard about this? What are we talking about here? There's 2 main things that make this really hard. And one is that there's just too darn many parameter settings. What do I mean by that? So we have the filter size in layer 1, the number of filters in layer 1, the filter size in layer 2, the number of filters in layer 2, the number of hidden nodes. And each of these have reasonable settings. Like, remember when we looked at the data, we thought that a reasonably small filter would work well. So filter sizes of 3 by 3 or 5 by 5 or 7 by 7, 9 by 9, 11 by 11, those are all reasonable settings for this problem. When you start looking at all of these, trying to figure out, well, what's the actual best setting of all of these parameters, you end up having to do the cross product, and those numbers can get very large. There's a few other parameters that we talked about maybe needing to try, and all of that works out to legitimately millions of possibilities. You say, okay, well, computers are pretty fast. Let's go try millions of possibilities and pick the best result and call that our model. I mean, why is this hard? One problem is that each parameter setting takes about 5 seconds to run on my computer, and that would be over 100 days to try all the possible parameter settings. So you're really not going to be able to just brute force this, and there's going to have to be some skill in deciding which part of this parameter space should I explore to get the model that I need that'll generalize well. And like I said, this is an easy problem. We have a very simple neural network structure. 5 seconds per parameter setting is going to be a very low number when you start moving into bigger and better models. So a big problem is that there's just too many things to try. And on even it's a pretty fast computer, you're not going to be able to try everything that you want to try. But even if you could, you can't measure these settings well. And in general, because we're dealing with statistical properties, this generalization bounds, watch the lecture if you don't know what I'm talking about, the evaluation you have of any particular setting is going to be incorrect. And in the case of what we're doing here, the standard deviation on the test set accuracy is about 1%. For any parameter setting, I can only know within about like 1% what its true performance is. It's going to be a problem figuring out what is actually the best. You can do 5-fold cross-validation and improve this to 0.5% of error in our measurements, but that's still going to make it pretty hard to figure out what we're doing. And now we have to do each run 5 times instead of 1 time. But another problem with neural networks in particular is that there's a lot of variance from run to run. And what this generally comes from is you have to initialize the neural network parameters to random starting values. So if you do the exact same run with the exact same parameters on exact same data, just with different initialization, run that multiple times, you're going to get very different answers. And so you can see these 4 charts represent 4 runs on exactly the same data with exactly the same parameter setting. The dark line is the training set loss, and the gray line is the validation set loss. Now you can just see, like, look at these two where the validation data ends up between these 2 runs. This one, it's close to 0.2. This one, it's a lot closer to 0.1. This one, it's maybe 0.18. This one's maybe like 1.6. And in fact, if you do this a bunch of times, you'll find that the variance in the validation loss can fluctuate up to about 10% from run to run just because of the parameter initialization. This is going to make it pretty hard to figure out what the best parameter settings are when you're trying to build your model. So what you're going to have to do is you're going to have to run the same parameter setting multiple times and average the results so that the one with the best average performance is the one that you select. And you use this average performance to help guide the searches that we're going to talk about coming up here in a second. And so, do a little bit of statistics, which we're not going to talk about here. If you do 5 repetitions, you can improve this variance by a factor of about 2. If you do 10 repetitions, you could improve this variance by a factor of about 3. So your mileage may vary depending on how much time you want to spend waiting. I'm going to do 5-fold cross-validation with 5 repetitions per fold, and that works out to evaluating a single parameter requires me to do 25 training and test runs, which works out to about 2 minutes per parameter setting on average. But some bigger parameter settings take a lot more time than that. That's what we're looking at here. So we got 3 things going for us now. We understand the problem and we've looked at the data a little bit. We got a little intuition. We've picked a model structure that is probably going to work pretty well. It's a proven thing. It'll probably do a good job on this problem. Maybe not the best, but it should get us pretty far. And then number 3, we've looked at some runs and we understand our ability to measure on this problem in this domain. We understand the variability of what's going on. Now we need to decide, okay, what are we going to do? How are we going to search? And there's really, I'd say, 4 options. In this video, I'm going to go through 2 of these options in detail and show you how to make decisions along the way. The first option is to do a grid search. We've talked that an exhaustive search isn't going to work. It's going to take hundreds of days to do that. But maybe you don't need to check every point for one of the parameters. Maybe you just need to create a grid and kind of like sweep far fewer parameter settings than you might like to try. So why would you want to do a grid search? It can help you understand which variables are important. It can help you find the boundary of the range that's important. For example, some parameters at very low settings are terrible, but kind of at middle settings are very good, and then at very high settings are terrible again. And so you can get a sense of the structure of your problem and which parameters are important in which ranges. But a grid search can be very, very, very slow. I'm going to go through an example of doing a grid search on this blink problem here in a second. Another thing you could do is a random search where you set the parameters to some value and then you randomly change them. You build a new model or evaluate that point through all the cross validations and restartings and whatever. Then you test if the new parameter setting is better than the old one. And if so, you kind of like update, sort of a gradient descent with random actions along the path. You could do this. You could let your computer stew for a while. It doesn't take any thought on your part, but it's going to take a long time to get good results. Another thing we're going to cover later in this talk is to do a directed search. And what this is to use your intuition to look at the output of each particular model run and ask yourself, what is this output telling me? Which parameter should I change and why? And so we're going to spend quite a bit of time going through how to do that interpretation and make good decisions so you can greatly speed up the process of getting to a very good model. Takes more of your time in terms of like human cycles, but the people I know who are absolutely the best at doing machine learning and producing awesome models, and I've worked with some very good people, number one, deeply understand their ability to measure, and number two, are fantastic at directed search. They can look at what the model's telling them and make just the right change to go in the right direction. The final thing you can do is AI directed, that is, build a machine learning model to actually direct this search, kind of like a meta thing. I believe it's going to happen, but computers haven't taken over the world yet, so I don't think it's happened yet. Anyway, whatever. We're not going to talk about that. Okay, let's get going. The first thing we're going to talk about is doing a grid search. And so here's the grid search that I ran. It had 245 parameter settings to try, 25 runs each. It took about 3.3 hours, something in that ballpark. And here's the parameters I tried. I completely ignored the second convolutional layer. I took all these extra parameters and set them to single values. And really what I explored was the filter size, the number of filters in the convolutional layer, and the number of hidden nodes. So that was my first step. What did I learn? This chart shows for all the different 245 parameter settings I tried on the x-axis ordered from the best to the worst. So the very best parameter settings was getting something like 94% accuracy. The very worst was getting something like 87% accuracy. Remember that our ability to measure is like 0.5% at best. So if you're saying, pretty much every parameter setting above that point is essentially tied with the best one, that statistically probably at a 95% confidence level, one of these is the best, but we don't know which one, something in that ballpark. If you want to look at the settings that tied with the best one, here's what the values were. So what can we learn from that? Look at the filter size. We could see 7 by 7, 7 by 7, 11 by 11, 5 by 5, et cetera, et cetera, et cetera. There's a lot of sevens there. One thing that pops out is that 3 never shows up at all. And so from this grid search, one thing we can conclude at this point is that a filter size of 3 by 3 is probably not good for this problem. We can stop considering that and speed up future searches. Then if we look at the next column of how many filters to use, the numbers are a bit all over the place, but there's very few below 20. I think there's maybe only 15 there that won. And I don't even see any 20s right now. So the number of filters is probably on the higher end of the range that we used. It might make sense that if we were going to do another step of this search, we would throw those away and add more parameters onto that side. Nodes, it's a little harder to see what's going on. There's some 5s there, there's some 30s there, some 35s. So what we might see here is that could be a correlation between this and the other features. We're not yet ready to make a conclusion about updating H or changing the range that we're going to explore H with. So you can do some exploration, and a great tool for this is Excel. You can make pivot tables and look at all different combinations of the features. One thing you might look at is a parameter sweep. In this sense, I've fixed the value of 2 of the parameters to pretty good values that I learned about from that previous table. And then I take the one parameter that I'm having trouble understanding and I look at all possible values of it from 5 to 35 with these things fixed. And so my interpretation of this chart is that with reasonable values of these 2 parameters, the number of hidden nodes, 5 is too few, 10 is probably too few. And then beyond that, they're all about within noise of each other. So the accuracy of this model is not super sensitive to the value of H once you're in a reasonable range. And my conclusion might be that, I'd want to have the fewest nodes that get me into the reasonable range so I can control the number of parameters while still picking up as much of the accuracy as I can. Okay, so once we figured out that the number of hidden nodes doesn't matter too much within a reasonable range, let's fix the value there and try to get some understanding of the other parameter values. Here we're looking at the number of filters against the size of the filters in the convolutional layer. This line here is clearly worse. That's the number of the filter size equals 3. We saw that on the previous slide too, that it's clearly an outlier in terms of performance. You can see that orange isn't great also. I mean, there's this peak up there that could be some kind of random noise. I think when these adjacent parameter settings vary so much, I'm a little suspicious that that really is the best accuracy among all of these. What I see instead is that, 7, 9, and 11 in this range are all pretty good. I mean, there's a little bit of variance there. There's some noise coming from somewhere. We can take that out later in the modeling process. But looking at this chart makes me feel that I would want to look somewhere in that range, number of hidden nodes in the 20-ish range, and create another grid and do more searches to try to find better values for these parameters and then start introducing other parameters. That's a kind of hybrid grid search where it's not just, you do a grid search, you look at the output, you kind of like learn something about your parameters and then launch another grid search. And this is the summary to some degree. We've eliminated some values of the variables that probably aren't good. Might say that somewhere in that range might be a good target. And so to summarize this process, you pick as many important parameters as possible, given the amount of time you have to run the first round of your grid search. You pick reasonable values of those parameters. You evaluate each combination using the cross-validation and the random restarts. You look at the behavior of the parameters across the sweeps. Just looking at the individual winners doesn't always tell you as much. It's important to look at how much adjacent parameter settings vary. And if you can learn a lot more from seeing consistency on adjacent parameter settings than seeing a bunch of things bouncing all over the place. If you see bouncing, then you're probably not doing something right. And like I said, we'll get to some techniques for what to do if you see a lot of bouncing here in a little bit. Get a sense of what's important, refine and repeat. That's the grid search, but it's very, very slow because if we wanted to add the second convolutional layer and try as many settings as we tried at this first go around, the way these things multiply is you end up having 12K more parameter settings to run on and 6.7 days minimum if the runs take, 2 minutes per parameter setting to evaluate. But as you're adding the second convolutional layer, they're gonna be slower just because there's more parameters in your neural network. So the amount of time to do that grid search is probably gonna be more than 6.7 days. The point is that relying on grid searches as your primary way of optimizing your model is gonna leave a lot on the table, and we're gonna show you how to do a little bit better here coming up. All right, so here we are. We understand the problem, we know our model structure, we know how powerful our measurement is. We've used a grid search to get slightly oriented on some of the basics of what's going on in this problem space. Now we're gonna go through how to direct a search to move quickly towards a very good model. And here are the steps. You start with a very simple parameter setting, or maybe the best one that you found in the grid search. I'm gonna start from something even simpler than that. You evaluate that parameter setting, just that single one by itself. But you look at intermediate values as well. You don't just look at the accuracy at the end. You look at the training set loss and how that progresses over the run. You look at the validation set loss. You interpret how the motion between these two types of loss occurs. You can also run the model beyond convergence because you can often learn a lot by looking at how the model performs after the point when you would normally have stopped it, just to see if it starts overfitting or it's something crazy starts happening. Then you interpret all these results and you use your knowledge and intuition. You use the toolkit you have in terms of how to change data, how to tweak parameters, what the parameters actually mean, how to tweak everything involved to make the right step. So you're not just trying random steps and seeing what happens, but you're taking the right steps. And so here's the initial parameter setting that I started my directed search from. And what this says is no convolutional layers, a single hidden layer fully connected to the input with 5 nodes in the hidden layer. The loss function is binary cross entropy, standard thing. I'm not going to experiment with that at all. I don't stop when the model converges. I run it for 5,000 iterations unconditionally, and there's no pre-processing on the data at all. I'm just putting the raw images in. And so, boom, here you go. Let me explain this chart a little bit. The x-axis is the number of iterations that the modeling run went for. And so every modeling run in this part of the video is going to run out to 5,000 iterations. This axis is the average loss on the indicated set. And then I plot one line for the training set and one line for the validation set. So in this case, you can see that the training set loss tracks the validation loss up until about this point. Then the loss on the training set is improving faster than the loss on the validation set. And you can see that the validation set here is kind of asymptoting. It looks like we've stopped making progress on improving validation loss around 4,000 iterations, but that training set loss is still improving. And so a simple interpretation of that is that at a certain point, somewhere around here, maybe somewhere around there, you're just really overfitting the data. You're not making much more progress on generalization, which is what the validation loss is helping you determine the generalization of this model. And so you can see that there's really not much point to run the model beyond 5,000 iterations. You're probably overfitting. And what's the interpretation beyond that? Like, how do I summarize this interpretation? I would say that this model has a high bias, and that is it is not able to represent the concept of eye open, eye closed very well. We're going to need a more powerful model, but it's not significantly overfitting. It's really just, kind of the generalization kind of stabilizes there, and we're not having a big problem with overfitting. And so what this clearly means we should do next is, think for a second, well, la-di-da, we should add more power to the modeling process. And what that's going to mean is starting to turn on all of these parameters over here to make the neural network able to represent more, but we have to do it in a controlled way. All right. The other thing I did at this point was I checked the test set accuracy with all the folds and restarts, and the test set accuracy at this point is 91%. So that's a little different than what I had reported previously, but it just goes to show how much variability there is from run to run and why you need to do cross-validation and average over a lot of restarts in order to make the right decision. This is where we start. Let's take the next step. The chart on the left here where it says previous setting is what we just saw. Down here, I'm going to indicate which parameters I change. So we've decided to put more power into the model. And the way I decided to do it at the first step was just up the number of hidden nodes. Hey, maybe we don't need any of this convolution junk at all. We just up the number of hidden nodes and we're done. So I run this and here's what I see. And this is actually not that good. If we were going to converge, the model would have converged somewhere around there. That value is better than any value achieved by the previous parameter setting in terms of the loss on the validation set. So probably better to some degree, but it's actually starting to overfit. That is, as we run more and more iterations, the validation error is getting worse. And so what I see from this is that we're not going to be that much better than the previous model, which was only 91%. So adding more power is likely to increase this overfitting problem and start to move it sooner and sooner and sooner. So my interpretation of this is that it's still high bias. We haven't corrected that problem in that this neural network with 50 nodes isn't able to represent the problem too much better than the previous one was. And we're starting to get overfitting signs. So continuing to push on this single variable we have been using, which is the number of hidden nodes, is probably not the answer. And my choice for the next step is to model the problem structure better. That is to have a neural network that is proven to be better for image problems. The way we're going to do that is by adding in the first convolutional layer. So here we see on the left, again, the previous setting. This is when there was no convolution and the number of hidden nodes was 50. And then for the new one that we're going to run, parameter setting number 3, we're adding in a small convolutional layer, even though we saw from the grid search that that's not going to be the best, but let's just take a start with that. We're using 5 filters and we're setting the number of hidden nodes back to 5 because going up to 50 didn't seem to be the right answer. And here's what we get. Oh my gosh. So that doesn't look very good. We can see that the validation error, the validation loss right around there compared to there. So adding the convolution layer made things worse. It didn't generalize as well as the previous setting. And it's very clear that we're overfitting. Around this point, doing more runs is causing problems. So this structure is powerful enough to overfit, but it's having a hard time learning what we want it to learn. Crazy overfitting in the long run. Okay, maybe not crazy, but that's what I typed when I was making the slide. So my interpretation is that at this point, we need to start bringing in some other tools. And so what I want to do now is do some of the standard overfitting prevention techniques, because I know convolutional networks should be much better at this than fully connected networks. Something's not working out, so let's apply those techniques and see what happens. So the techniques I'm going to use is I'm going to turn on dropout, that dropout layer before the fully connected layer, and the dropout I'm using is 50%. I mean, that's another parameter we could have tuned, but I'm keeping things simple. And I'm doing some basic data processing to the input data before feeding it to the neural network. And that is, I'm normalizing the mean and the standard deviation of the inputs. Each image I normalize on its own. I'm not doing a full data set normalization, whatever, blah, blah, blah. And so when we run that, kaboom. So just by the simple techniques to avoid overfitting, we end up in a much, much better place. Now this one, we can see the validation error is the best we've ever seen. And the properties of this are really beautiful in that it's not starting to overfit no matter how far you run it. So I like the way this looks. My interpretation summary is that this is a very well-behaved run. And so you want to ask yourself, are we done? And so I've gone and looked at the test set, and I try not to look at the test set too much, but because this is so well behaved, I'm like, ooh, let's go look at that and see where we're at. 93.95%, so almost 94%. With just a very little bit of tuning, we went from 89 to 94. This is competitive with the best thing that the grid search found. In fact, it would have tied with it, but we got here much, 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 much faster. But we're not done yet. Let's not quit there. Let's figure out what the next step is. And every time I see a well-behaved run, my instinct is to add more power. So how are we gonna push it and try to get a model that's gonna go further without going too far and ending up back in that overfitting state that we were in on the previous parameter setting? So one way to add power is to increase the number of hidden nodes. So let's just turn that back up and see what it does. Okay, so what can we tell from this graph? Let's look at the interpretation. The first thing is that it actually does look better. The validation error, if we were converging, it would converge somewhere around there. And it's a fair bit better than where the previous version would have converged. So I'm happy with this. And, in the previous runs where we did the grid search, we saw that something in the 30 ballpark is probably fine. So that's a good step to take. But then the other thing we see is that, well, as we continue running past that point, the model does start to overfit, which is probably okay, but it makes me think that for the next step, we should apply a little bit more to help with the overfitting, because we haven't used all those tricks yet. And this chart says like, hey, that could be a little bit of a problem still. So let's try to get things even more under control. Okay, and here's the point when I decide to do some data augmentation. And remember, if you take a right eye and flip it, you can turn it into a left eye, completely anatomically okay. It's a very, very safe thing to do to your data. Basically allows us to go from 4,500 training samples to 9,000 training samples. It'll slow things down a little bit, but it'll help with our measurements, and it will help the model get further before it starts to overfit. So that's what I'm going to do here. And here's what that looks like. You can see that if you look at the convergence point, that this new model has a little bit of weirdness going on there, but overall it's converging about the same or a little bit better, and that the downstream behavior is actually a lot better in that it's not overfitting as much as the modeling run keeps going. Just makes me happy, makes me think things are a little bit better behaved. So jitter around convergence, but overall this looks better than the previous run. In fact, it looks a lot better, and I'm kind of excited about this augmentation. So I go and check the test data again, which is probably a little bit too soon. I feel like I just checked it, but 94.24%. That's good. Hard to know if that's statistically significant better than the previous run, but I'm feeling good about seeing a 94 there. And the next step is, bam, we're ready for more power. And so what's the power we're going to do this time? I'm going to do two things at once, which generally I wouldn't do. I do things one at a time and do the interpretation. But the first thing I'm going to do is take the filter size of the first filter and move it up to 5 by 5. That's motivated by a couple things. Number one was the grid search that we did previously, where we saw that 3 by 3 wasn't working so great. And number two is a sort of general idiom that you would use a large filter, then you would use a smaller filter. I don't know if that's super true, but it's just like my instinct. The other thing that we're going to do here is I'm going to do a very small sweep to make a decision about where to go next. I don't have to try just one thing. I'm going to try 3 settings. So 2 convolutional layers. The second one is 3 by 3. And I'm going to look at using 10, 20, or 30 filters in that second layer. And everything else is the settings that I had found previously to be working well. So here we are with 10. That's looking pretty awesome. You can see that point right there compared to this point right there. Immediately, I start to think that having 2 layers of convolution is a good thing for this problem. F equals 20. That's even a little better still. Later conversion properties don't look great, but really, zooming in on this area, I'm feeling pretty happy with that. The third one, well, that looks similar. Using 30 filters in that second layer. So I don't know, I'll probably end up selecting something in the 20 ballpark. My interpretation is that these 2 convolutional layers are a better match for this problem, and that overall it's pretty good. So we're in a place where we can, you know it, try to add a little bit more power. All right, so the final thing I'm going to do here is let's tune up that number of filters in the first layer now. We previously had been trying 5. Now let's throw in a few more values. And notice I do, this particular run, I do 5, 20, 30, where previously I would do 10, 20, 30. The reason I do 5, 20, 30 is because I've already run with F1 equal to 5. And so, my guess after working with this problem a little bit is that I'm not going to learn a lot more by running 10. So I'll just compare 5, 20, and 30. And if I see something funky in the data, then I might go and look at another point before making a decision here. But it turns out there's nothing funky in the data. This parameter doesn't seem to matter too much. You might say that this one over time overfits a little bit more is what that looks like, but this one's a little bit more jittery, which isn't a good behavior property. So you could pick whichever one you want. I picked F equals 20, looked at the test set accuracy, and it's looking more like 96.8. That's fantastic. And when I say with convergence check, that means I stop the run right there. I'm not running it all the way to the end. So we're looking like we're in pretty good shape here. This is parameter setting number 8, and we've gotten a lot further than we're able to get with the grid search. What should we do next? Well, there's this thing called residual networks, and why the heck aren't we using those? Why not use these modern techniques and add a residual block between the 2 convolutional layers? And if you don't know what that means, please go watch the lecture that I have linked below about neural network architectures. That is an hour and a half about going through all of these things and what they mean and what they're good for. But let's just say a residual block is like a fancy convolutional layer with nice convergence properties, more power, and putting together a bunch of residual blocks has led to human level performance at many computer vision problems. So they're the right thing to do. But when I add a residual block between those 2 convolutional layers, here's what I see. Some problems. There's a lot of jittering and noise in what's going on. Things become less stable and it's like super overfits. So is this the right thing to do? I'm not sure. My interpretation is that adding that residual block is adding a little bit too much power and it's making the modeling run unstable. It also makes the runtime much worse, more than double the runtime without the residual block. So I'm starting to think maybe this residual thing isn't absolutely necessary for this problem. And taking a step back, why did I start very simple instead of starting in this place with this fancy residual block? Well, it's because with more power, you have more jitter from variance. You get less information from each run because of this. Each run is slower, and it's easier to interpret the intermediate results if things are well behaved than if they're not well behaved. Because going from this residual thing, my belief now is that, with this residual block, I need to remove some power. But where do I go? What do I do? It's harder to tell when you throw everything at the problem in the first step. So that's why I like to build up from simple things. The next step here is take a step back and look at mistakes. Nobody likes to look at the data, but at some point, the best thing to do is look at where your model is having trouble. Where are the mistakes? There's 17 mistakes on closed left eyes. That is calling a closed eye open when it's left. There's 26 mistakes on closed right eyes, open left eyes, open right eyes. When I look at these numbers, I'm not like super worried that there's something crazy going on where all the mistakes are on one type or another. I mean, this closed right is higher than the others, but that could be explained for a lot of reasons. So I'm not thinking that the model needs to be tuned for a particular type of mistake at this point. Let's go to the next step and actually look at some data. And so here are closed left eyes that the model got wrong. And when I look at these, I'm like, wow, these are pretty hard. There's some pretty grainy images there. This one, I can't even see anything. This guy has glasses. So, these are tough examples. And these are the things that are mistakes. This one, closed right eyes. What the heck is this thing here? This guy's not centered very well. Open left eyes, very harsh shadow along there. This guy is open. I don't know, man. That looks pretty close to me. Open right eyes, another super harsh shadow, really overexposed, really underexposed. So here are my observations, a lot of different problems, things to work on. Probably makes sense to go and correct some of these things through data normalization, data augmentation in certain ways. Okay, and my next step after seeing this is to hand it over to you. You've seen the basics of model tuning. You know why it's hard. You know what grid searches are. You know how to interpret the results. You know how to do a directed search to some degree. You should be prepared to do basic model tuning and build professional models that will generalize well and solve your machine learning problems. And summary overall, your goal of model tuning is to get the highest generalization accuracy you can. Invest in understanding the variance of your modeling process so that you understand the measurements that you get along the way so you can make good decisions. Too many parameters to be exhaustive, so you need some strategy, whether it's a grid where you skip settings or whether it's directed by your understanding of modeling and your intuition. Grid search can help you kind of throw away some junk to get you started, but then a directed search using human intuition is really the right way to go to get the best model that you can get. And of course, nobody likes to do it, but look at the data. I think the two things that I see the most in my career as a professional machine learner is that people ignore this. They don't understand the measurements that they're getting, and they really just don't want to look at the data. And adding those two things to your arsenal can very, very quickly make you a much better modeler. All right, it was quite a journey. Thanks for watching. Please subscribe. I'll be posting more content like this. And please leave comments if you think I messed up something or if you have some other good techniques you'd like to share. I'd love to see what you have to say. All right, everybody. Peace.